Good afternoon. I hope you have an enjoyable week. And today, we are going to be on mechanical engineering. Wk04. Today's a Friday, week 2. Well, week 2 already. Okay. And Friday. So the agenda for today is we are going to continue. I'm going to restart from scratch. Okay, continue the example on force undamped vibration. Then after that, we are going to go into performance measure performance measure for underdamped free vibration. Okay, we are going to look at performance measure for underdamped free vibration. Okay, and I hope if we finish, I hope to write a come on, Eugene. I hope to summarize the topic. Okay, so it's going to be the end. Okay, I'm not going to do force damped vibration. I'll leave that when you go into the vibration course when you take in your 3rd or 4th year. Okay, depending on which program you're in. Right, as I said, I will restart on the problem that I have introduced to you yesterday. Okay, so we are going to look at a example on a forced undamped vibration. So to make things clear, right? To make things clear, if I draw the schematics of it first, if I were to draw the schematics of it, okay. So now this is not the question, by the way, okay. This is just the schematic of the system. Well, right now here, this is the schematics of the system. Oh, hold on. I did not know. Did I start recording? I did. Okay. Schematics of the system. So I'm going to break it into stages. What does it look like? Okay. So stage 1, you have a spring. Okay. Then from stage 1, you have a spring with a known stiffness. In stage 2, we have a spring, but we add a mass. Okay. Put on a mass. Now the deflection we have over here right? This deflection you see over here, I'm going to call it, okay, that symbol. So that deflection, which is delta, This is known as static deflection. Okay. Then on stage 3, we have the entire system. Okay. But we are going to incorporate we are going to put a force okay, and this force will be equal to F naught sine omega t or omega naught t. Okay. And then from here, during the excitation or when time, okay, this is when time is greater than 0, okay, the thing will keep on, the force vibration will be there. Okay. We will not remove it at all. Okay. The vibration is to be there. Okay. Now, what I'm going to do now is I'm going to superimpose the question into a problem now. And I want you all to see the schematics on how the question fit into this diagram that we have just drawn from left to right. How does it work? Okay. So here's the question, okay, which we have written part of it. Okay, so we have a system now. Right? The system, we have a beam, right? And then we have it simply supported. This is our point A. This is our point B. Okay. So for what I'm going to do, because I'm so used to writing displacement is in the X, I'll call this my X and I'll call this my Y. Okay. My X, my Y. And we know that at point A, right, because it's pin, right, X is equal to 0, Y is equal to 0. And on the other side is a roller, right? So for this case, X is not equal to 0 relative to the transformation I've drawn out here. Yeah, whatever we do is all relative to our transformation. And then Y is equal to 0. By the way, did anyone look under the bridge? No, not at all. Okay. So if you look at reality, right? How does a beam like this look like? Okay, let's say now you're going to design a beam in real life and you want the fixturing to be like this. How does it look like? Is it necessary to put a roller under the bridge? That's the thing, right? I thought it was, okay? I have to have a roller. The fact that we call a roller does not mean it has to be on wheels. Okay, I literally take the words for it. Like in English, this is the width, this is the depth. Yes or no? English. But in real life, depending on where your frame of reference is, this can be your depth and this can be your what? Your width. So in real life, how this look like? Okay, if you were to design a structure like this, how would this look like? Okay, so these are your support. And on the other side, this is the other side of the support. So this is the support at point A, and this is the support at point B. Then after that, you put your beam. I'm going to change color. You put your beam down here. That's it. There's no roller. Okay. The fact that we call it a roller is because we allow the degree of freedom to move in this direction. Okay, so don't go under the bridge, start looking for rollers. Are we clear? No roller. Okay, I did not know that. I went under the bridge. Okay, and like, oh, is that it? Okay, right. Coming back to our question now. So on the bridge or on the beam, right, we are going to place a motor. Okay, on the beam, we're going to place a motor. Okay, so on the beam, we are going to place a motor. So when we place a motor at the center, right? So this is our pin. This is our roller, right? So we are going to put a motor on the beam, and the motor, this is exaggerated, okay? Cause the structure to deflect. So now I put a motor. Okay, that's a motor. The motor has a weight of 150 pounds. Okay, 150 pounds. And given to us, the deflection over here, okay, is equal to 1 inch. Okay, the deflection is equal to 1 inch. So when you look at the schematics, right? When you look at the schematics, what can you see? Can you all figure out which is stage 1 and which is stage 2? Yes or no? So you can see where is your stage 1 and where's your stage 2, yes or no? Right? So when you see a question like this, when you put a mass on top, you see a deflection over there, you understand what actually means. Right? Then the next one is where stage 3 comes. Now, have you all seen a motor before? Right? An electric motor. So when you turn on an electric motor, it usually don't vibrate. Okay? Remember I told you guys about laundry, yes or no? Right? Right? Those things, when you go into spin cycle, right? When you go slow, and then when you go quicker, right? It will vibrate more and more. Then at its optimum RPM, no vibration. Right? If there's a vibration, the dryer will walk up the laundry man. You understand what I mean? Okay. So now, what we have now is how do we get the motor to vibrate? Okay. How to get the motor, and it's not just turning on. Okay. How? Now the question is how to get the motor to induce a forced vibration. Okay. So now I'm going to draw, I hope to draw the motor in 3D. Okay. So this is the motor in 3D now. Okay, my 3D is a bit off, but you know, yeah, you will see something like this. Okay, now this is your motor. So what we're going to do to the motor, this is a motor shaft. Okay, this is the motor shaft. We are going to put an arm